We're going to talk about this special number e, which is called Euler's number here. First of all, we're going to estimate the value of the following limit by completing this table of values. So I've given you the limit here, and I've also told you what values you're going to sub in for the x to estimate what that limiting value is. So our x has to approach infinity, so I've picked larger and larger values of x. I stopped at 100,000, but you could go bigger than that if you wish, and if your calculator can manage those numbers. So we're going to stick the 1,000 in for this first part into our evaluation here. I'm just going to use direct substitution to evaluate what that's going to be. So I'm going to take 1 and I'm adding 1/1000th to it, so it's just over 1. A number just slightly bigger than 1 is what I'm trying to say there, and then that's going to be all to the exponent of 1,000. So you can put that into your calculator and get an approximation for that, and then do the same with 10,000 and 100,000. All right, I have filled in my chart here, and you can see these values of our limit are changing. They're increasing, but they're increasing only by a tiny little amount. And in fact, I did 10 million. When x is 10 million, this is what my calculator said. So we are getting closer and closer to a specific value here when we calculate this. And in fact, the value of this limit is approaching this value here. Now, how I got this actual value here is I found on my calculator an e to the x. Okay, e to the x. So e stands for this particular number. This is e to the exponent of 1. So for me, I put my base or my exponent of 1 in, and then I hit the e to the x button. Some of you can just do e to the x and then put the 1 in for the exponent, and it should give you this number. This number really is e to the exponent of 1. So look for the button that is e to the x and make the exponent x equals 1 there. Okay, so that is Euler's number. If we use that base on our exponential function, if we do y equals e to the exponent x, when I graph that function and then I graph the derivative, that derivative lands right on top of the original function. This is a the derivative is itself here. So like pi, e is just a symbol used to represent this particular value right here. And this limit that we just calculated is what we call the fundamental limit of calculus. So e is equal to this limit, and that limit is also the same as this one here. And I'm going to put a link on our Google Classroom to a nice little video that goes through Euler's number in more detail if you're interested. I'm sure if you go on and take calculus in university, they're going to go back over this stuff again and reiterate what this is all about. But there's a nice little video that explains why these two limits are actually equivalent to each other. So if f at x is e to the exponent x, it is a function whose derivative function is itself. In other words, f prime at x is also e to the x. So the inverse of f at x equals e to x is now when we think inverse function, that's not derivative. The inverse function, remember when we did any exponential function? So let's say we had f at x equals 2 to the x. The inverse of that was the log of x with a base of 2. That was the inverse function. So in this case, when I have e as my base to the exponent of x, the inverse of that is the log of x with a base of e. Now, anytime we have a log with a base of e, that's when we can replace that with the ln. This is ln. So I don't like to use the printed letter L because that looks like a number 1, and then people are like, why are you writing in? Because that also looks like the letter I. So I do usually make that a cursive when I handwrite that. So that log with a base of e, the shortcut, is called ln, and so it's pronounced ln, pronounced like what you grow in your backyard or front yard, or maybe you don't have a yard, but it's at the park or at the school, pronounced ln x. Okay, now remember when we had no base written? I'm just going to use a different color here. When we had no base written at all, if we had just the log of x, that had a base of 10. This was base 10, and that was called the common logarithm. Common logarithm. Well, this one, when it doesn't have a base of 10, but because e is such an important and special number, it has its own notation for it. It's the ln of x, and this one is called the natural logarithm. So you could take the natural log of both sides to help you solve things as well. Logarithm. All right, so graphically, the inverse of an exponential function is that, or any function, is that reflected function in the line y equals x. So I have my graphs of e to the x, my exponential function, and then if I were to sketch that y equals x line, oops, y equals x line here. Oh, I don't know if I'm doing that all that well, but this is supposed to be the line y equals x. Remember, the one is the reflection of the other. So this is just the graph of ln x. So you'll see it looks very much like the logarithm function, because it really is a logarithm function. It's just a special logarithm function. One other thing I wanted to point out is if you have, instead of just e to the x, if you've got this exponent being an actual function itself, then think of that as your chain rule. You're going to have the derivative of your e to the x, which is just e to the x, or in this case e to the f of x, times the derivative of what's inside. So times the derivative of the exponent right here. So we did do that on our exponential derivative lesson, but I wanted to point that out here as well. All right, let's do a couple of quick examples here. All right, so this very first one, I have e to the exponent 3x. So 3x is like its own function. So I'm going to take the derivative of that exponent. The derivative of 3x is just 3 times the original function. So the derivative of e to the x is just e to the x. The derivative of e to the f at x is e to the f at x times the f prime at x. So that's what we have here with that. All right, the next one here, we've got f at x being the square root. Now I'm just going to change that square root to an exponent of 1/2. So we're going to have e to the 5x all to the exponent 1/2. And then that's going to give me an exponent, if I use the exponent property of multiplying those together, 5/2 x as my exponent there. So when I take the derivative of that, I'm going to take the derivative of the e to the exponent 5/2 x, which is itself, but then I need to multiply it by the derivative of the exponent. And the derivative of the exponent is just 5/2. So I'm going to have 5/2 times e to the exponent 5/2 x. Okay, now our last example here, we've got y. It actually is a product rule because I have this function and then I have this function. So we're going to have y prime, or dy dx, the derivative of the first, so 5 times 4 would be 20, x to the 4. So there's the derivative of the first times the second, plus, and then we want the derivative of the second. So we have the original 2, which is just a multiple, so it's still going to be there. The derivative of the exponent 5x would just be the 5, and then we would have that multiplying the original e to the f of x, which is e to the 5x. The derivative of the second times the first. Okay, so let's just tidy up here for a second, and then we'll see if we can factor that at all. 20 times 2 would be a 40, x to the 4. I could factor directly from here, but I'm just, to make it a little bit simpler for my brain, just going to tidy that up. I've got a 2 times a 5, which is 10. 10 times 4 is a 40 as well. and then we have an x to the 5 and an e to the exponent 5x. And then if I look at what's common between those two, 40 is definitely common, e to the 5x is common, and then the lowest power of x is x to the 4. So I'm going to go 40 times x to the 4 times e to the exponent 5x, multiplied by 1, because I need all of that, and then plus, I just need one more factor of x out of that. One more factor of x out of that, yes. Okay, and so then that would help us find our critical numbers. All right, I hope that makes sense, and I hope you get along fine with this.